Yeah. So today we will be discussing aromaticity. So this is a special property of organic compounds. So those compounds which are aromatic in nature are highly stable. So why they are stable? Because whatever the electrons present here, whatever the pi electrons we are seeing in these aromatic compounds lies in lower energy state, that is in bonding molecular orbitals. So that makes it to be more stable. So whereas in anti-aromatic compounds, the pi electrons which are present here, that will be in the anti-bonding orbital, which is higher energy state. Therefore that makes it to be unstable. Okay, and we have three types of compounds now. One is aromatic compounds which are highly stable because the pi electrons present in the lower energy state, and next one is anti-aromatic compounds which are highly unstable because the pi electrons present in higher energy anti-bonding orbital, and the next in between these two we have one more type of compound, those are non-aromatic. So total three types. One is aromatic, yeah, so total three types I am saying: aromatic, non-aromatic and anti-aromatic. Okay, so what is the stability order of these compounds? I am saying aromatic is highly stable, then non-aromatic and least stability is for anti-aromatic. Okay, and you can just remember these aromatic compounds generally diamagnetic in nature. What I am saying, diamagnetic, and anti-aromatic compounds, these are paramagnetic. Okay, and this non-aromatic compound depend upon the compound to compound. Okay, so now you will get more clarity when we discuss with some examples of aromatic, anti-aromatic compounds. It will gives you clear cut idea on all these three things. Okay, so now again these non-aromatic compounds again classified into some other things we will discuss later. First of all we will get clear about this aromaticity first. Okay, so what I can say, a compound is said to be aromatic if the compound is cyclic. If the compound is cyclic, first condition I am saying it should be, compound should be cyclic compound, and it should be planar. The compound should be planar. It means either it should contain sp2 or sp hybridization. Okay, there are some compounds which contains sp3 hybridized carbon also, but that won't involve in the conjugation, therefore that is also considered as aromatic. Okay, cyclic, planar, and next complete conjugation of pi electrons. Third condition is what? Complete conjugation of pi electrons here in the system. And fourth condition should be compound should follow 4n plus 2 pi electron rule. Pi electrons should be, this many electrons should be present in the given compound. So what do we mean by n here? So you can place n as 0, 1, 2, 3. If you put 0, the 4n plus 2 means 4 into 0, it becomes, if it is 0 you are going to get 2 pi electrons, if it is 1 you are going to get 6 pi electrons, if it is 2 you are going to get 10 pi electrons, like this. Those system containing these electrons, by satisfying first three conditions along with the fourth condition, considered as aromatic. Okay, is this clear up to here? Yeah. So now these four conditions, out of these four conditions only first three conditions are satisfied, these three conditions are satisfied. Along with that, instead of this fourth, I am writing one more extra point here. If they follow 4n pi electron rule, it means 4n pi electrons are present, 4n pi electrons are present, then we should call them as anti-aromatic. Okay, so if these rules are followed, first four, that is aromatic, instead of following that fourth rule, if this directly along with the first three, if this fifth rule is followed, we can say anti-aromatic. That's it, clear now? Yeah. So now the best example or the first example of aromatic compounds will start with the benzene ring. Okay, this is what benzene. So benzene, if you look here, it has 6 carbon chain, it is cyclic compound. So it is satisfying the first condition of aromaticity. Okay, next, so it should be contain planar carbons. So all 6 carbons are sp2 hybridized in the benzene. Okay, sp2 means what is the geometry? We can say trigonal planar. trigonal planar. So name itself saying the compound is planar, right? Yeah. So complete conjugation of pi electron should takes place. See, this pi electron will shift here. When it is shifting here, this can move here and this can move here. See, complete ring cyclization, like ring pi electron conjugation is taking place right now. So fourth condition, that condition is also satisfied. And what is our last condition here? Should contain 4n plus 2 pi electrons. See, how many electrons are there? 1, 2, 3, 4, 5, 6. 6 pi electrons means what is it? 4n plus 2. If n value, if you put 2, so you are going to get 10. If you put 1, so 6 pi electrons we are getting now. So it means it is satisfying all the first 4 conditions. So I can say this is aromatic. Okay. So hope this is clear. Now I told you one more thing. I told you that aromatic compounds are diamagnetic in nature, right now. So how we are saying they are diamagnetic? So look at here. There is some rule called Frost-Muslin rule or Frost-cycle rule. It means you just take one sphere or one like something like round shape here. Okay. So try to take your polygon, like consider your cyclohexane ring as a polygon here, and try to insert, like try to attach all these corners to the ring, I mean this circle whatever you have taken, like this, like this. Okay. And now try to divide these into equal halves. So equal halves means I can get like this and I can get like this, right now. Okay. So now this is the energy level you can consider. So if any orbitals present here, if any carbon comes here, I can say those carbons are like orbitals there, we can say non-bonding orbitals. If they are present below this line, they are bonding molecular orbitals. Okay. So what I am saying here, we have one carbon here now, so I am writing one orbital here, and we have one orbital here and here, and this one carbon, so respective orbitals I am writing here, like this. Okay. So if any orbital lies on this horizontal line, you should call them as non-bonding molecular orbitals. If lies above that line, anti-bonding. If they lies below, bonding. That's it. So this is the energy coordinate I am saying. So which is lower energy states? These bonding molecular orbitals. Now how many electrons we have? 6 pi electrons. First fill in the lowest energy level. This is the lowest now. So 2 electrons is filled. Next higher level, here 1 electron. This is a degenerate state, here also 1 electron. If I have only 4 pi electrons, you should fill like this, you can say paramagnetic. But how many we have? So 1 more here, 1 more here. All 6 pi electrons are paired up now. So I can say benzene is in aromatic in nature because of all pi electrons are paired up here. Like this, we can also explain whether they are diamagnetic or paramagnetic by looking at the Frost cycle. Okay, clear now? Now look, aromatic compounds, why they stable I told you, their pi electrons lies in the lower energy bonding molecular orbitals. Okay, and if it comes to what I can say anti-bonding, I mean anti-aromatic compounds, those pi electrons will be in the higher energy state, that makes it to be unstable, right? Yeah, it is clear now. Now I will be giving you some examples of like examples that we must identify whether aromatic, non-aromatic, anti-aromatic. Okay, just I wanted to start this with these things, and the next this thing. So just write along with me so that your time will be saved and you can practice along with me now. Okay, 3-member rings are over. Next 4-member ring I am writing. Like see, cyclic compound starts from at least 3 carbons, so that's why I mentioned 3-member ring. Okay. So first one, tell me, is it aromatic or non-aromatic? What is it exactly? So look at here, you have sp2 carbons here, but what about these? sp3. So it is non-planar compound. So you can say directly non-aromatic. Okay. And what about this? See, this is sp2 carbon, and this is also sp2. All the carbons are sp2. So it means compound is cyclic, compound is planar, and you know complete conjugation takes place. How it takes place? See, this pi electron will jumps here. When it is jumping, so it is making a bond between this carbon and this positively charged carbon. Therefore, this carbon becomes vacant, like positive charge. Okay. So what I should write in this case now? Like this, cyclopropyl, and shifting a bond here makes positive charge here. Next, again if I shift this here, you are going to get positive charge here. Like that, complete conjugation is taking place. So third rule also satisfied. What is the fourth rule? 4n plus 2 pi electrons. Okay, directly do not go 4n plus 2. First of all, come from very basic cyclic planar complete conjugation, then 4n plus 2. Now look, 4n plus 2, if n value is 0, 2 pi electrons is there now, so it is satisfying. So I can say this is aromatic. This is a smallest or simplest or smallest aromatic compound you can make. Okay. Next, what about this? It has carbons like this. See, this negative charge can participate in the delocalization. It makes compound is cyclic, compound is planar. Why I am saying all carbons are sp2 hybridized, planar. Okay, and it has cyclic conjugation. Continuous conjugation will be there. In the place of positive charge, you are going to see a negative charge. That's it. Okay, so it means what I can say. It is having how many pi electrons? This 2 pi, and this is also becoming pi. See, if you want to write, just write one conjugative position. See, always remember, whenever you have a negative charge in the given compound, so start your delocalization from that negative charge. See, from here I should write. So when I am writing like this, you are making a new bond here. So these pi electrons shift here. Okay, so that you can get a pi bond here, negative charge here. Right now, again you shift negative charge here, the pi bond will shift here. Like this. Writing conjugations is very, very tricky and a very important thing in order to write reaction mechanisms properly. Yeah. So complete conjugation is taking place. So I can say this is having complete conjugation, and with how many pi electrons? These 2 pi electrons here, 1, 2, and this also becoming pi bond now here. See, this is becoming negative charge, this is becoming pi. So I can count these 2 also. So total 4 pi electrons are there. It means it is satisfying 4n pi electron rule. So 4n pi electron rule along with the first 3 rules. So I can say it is anti-aromatic. So it is anti-aromatic. Right. Okay. Next, tell me about the other things. This one, see, these 2 carbons are sp3, so non-planar, so non-aromatic. And what about this? Like this delocalization taking place. So complete conjugation is there with how many pi electrons? 4 pi electrons. So cyclobutadiene is an anti-aromatic compound. Okay, so you can say anti-aromatic. What about the next one? Yeah, what I told you, whenever you have negative charge, start delocalization from movement of electron from that. Either you can start from here or here, no issues. But do not go to the negative side. Come this side, like this. Okay, this will shift here. Right now, so what you are going to get? Double bond here and negative charge here. Already you have a negative here, right? And after this, again this negative charge might shift here, and this becomes here, like comes here. Okay, so again you have double bond here, negative charge here, negative charge here. Again this negative charge will shift here and pi bond shift over here. So like this. Like this. Complete conjugation is taking place or not? Yes. Okay. So now due to this complete conjugation, I can say compound is having how many pi electrons? 6 pi electrons. So 6 pi electrons means we know it is a Huckel number. Right now try to remember like 2, 6, 10, 14 like that you remember for Huckel number. So it is a aromatic compound. So this is aromatic I am writing. And what about this? Same, whatever story you have studied, apply there. All carbons are sp2. Planar. Yes, next. Takes place. How it takes place? See, pi electrons will shift to the positive charged empty carbon. Okay, comes here. Again, this pi electron will shift here. Therefore, what happens? Positive charge comes here. Like that, complete conjugation is possible in this case also. Right now, so this is also aromatic compound with how many pi electrons? 2 pi electrons. Like that. Okay, so aromatic I can say. Is that clear? Next. Now we have 3 over, 4 over, next 5 member rings. Like this. Tell me.
First one is non-aromatic.
Non-aromatic. Yes, this is sp3. Next.
All are sp2 hybridized.
All of them are
sp2 hybridized.
okay. sp2 hybridized. Next.
And then
Conjugation takes place like this. For positive charge comes like that. Complete conjugation is possible. Next.
It has 4 pi electrons.
It has 4 pi electrons. So it means
It is an
anti-aromatic. Okay. What about this?
sp2 hybridized planar.
Yeah.
Complete conjugation takes place.
Yeah. So this can shift here and comes here like that. It has 6 pi electrons and aromatic. Right now. So now I just want to clear itself here itself that what is the use of studying this aromaticity. Now look at here. See, I am giving a compound like this. So giving chlorine here. Okay. For example, instead of this, if I mention AgCl, NaCl plus AgNO3, what happens here? What is the reaction taking place here? So AgCl forms AgCl precipitate here and NaNO3 is formed here. So AgCl white precipitate you might be seeing some precipitate is formed here. Okay, but you know if you are doing the same reaction with this compound, whether this precipitation formation takes place or not, this will be the question. AgNO3, they will give 4 reactions. Which are the following precipitate upon treating with AgNO3? I am giving you this one and whatever we have studied previously, that 3 membered ring, giving this 2. So tell me, out of these 2 which will form precipitate? Which of the following will precipitate? So tell me out of these 2 questions, A, B. So how can you identify these? See, we know carbon and chlorine, which is more electronegative? More electronegative now. So bonded electrons will taken by chlorine. So it means chlorine going as chloride ion precipitating with the Ag. So as AgCl, if it is precipitated, what is the remaining piece here we are having? Cyclopentane, like diene with a positive sign here. So now look at the nature of this compound, whether what is the nature of this compound? Aromatic, non-aromatic, anti-aromatic. So we know it is anti-aromatic now. What is the stability order of aromaticity?
Aromatic, non-aromatic and then
Anti-aromatic. Least stable now. So this is a non-aromatic compound becoming anti-aromatic. So anti-aromatic is highly stable now, highly unstable now. So will it forms? No, it won't form because it is highly unstable. Therefore, the reaction won't takes place. Okay. So this is the application of aromaticity. See, if anti-aromatic compound is formed, therefore no precipitation in this reaction. No reaction you can say, this won't formed here. Okay. Now what about this case?
again Cl is more electronegative.
So you are going to get a carbocation like this and NO3 salt here like anion here, AgCl. So now tell me what is the nature of this compound? This is aromatic now. So if this is aromatic, then formation takes place. So precipitation takes place in B but not in A. Is that clear? This is the application. Now this is one application. Now I will be giving you one more application here. See, I am giving you 5-membered rings, okay, having hydrogen atoms here, okay, and 3-membered ring having hydrogens here, okay. So now out of these two, A and B, I have mentioned these hydrogens now, A hydrogen, B hydrogen, which is acidic here or acidic order, acidic nature order. Order of HA and HB. So tell me, which is more acidic out of AB? Yeah, acidic nature means what? A compound is considered to be acidic if it releases H plus ion. So now if this fellow releases H plus ion, if this compound releases H plus ion, so what is the resulting species you are going to get? What? H plus goes out. So the bonded electrons remains with the ring only now. So what is the species? Carbon anion. Negative charge is generating, right now. So you should say that as conjugate base. So what is a conjugate base formed here? Double bond and negative charge here, right now. So this is what formed, and in this case also 3-membered ring and a negative charge here. Now look at the stabilities of these two things, like conjugate bases formed here.
This one is more stable.
This is more stable because it is aromatic. But what about this? This is anti-aromatic, right now. It means formation of anti-aromatic compounds is not possible or highly unstable. Therefore, it is weaker acid. The respective compound is weaker acid. But here, forming a highly stable compound, so formation is easy. So respective compound is more acidic. So you can say HA is more acidic than HB. Okay, this is also based on what? Applications of aromaticity. Clear now this one also? Yes. Next, yeah. So we have some compounds in which heteroatoms are involved like this. So the name of this compound is called pyrrole. What is that? Pyrrole. And this one is furan. And this one is thiophene. Pyrrole, furan, thiophene. All these are heterocyclic compounds and aromatic. Okay, and you know they will ask which are the following is non-benzenoid aromatic compound. Is there any benzene ring? No. So these all these things are considered as non-benzenoid aromatic compounds. Okay, so benzenoid means generally they should contain at least one benzene ring in that compound. Okay, right. Next 6-membered rings we have. Benzene we discussed, and along with that I can replace, see, CH is a like each of this, here we have CH. I am replacing one CH with one nitrogen like this. What is the name of this compound? Pyridine. So pyridine is also aromatic. Okay, and next. What about this?
It has one benzene.
So tell me, aromatic or not? Aromatic. See, 6 pi electrons here and 2 pi electrons here, and lone pair also become pi. So 10 pi electrons are containing in this system with cyclic, planar, complete conjugation right now. So this is also aromatic. Okay. Yeah, next. So these compounds you might be seeing in the amino acids, like you know, in amino acid biomolecules chapter you will be coming across this kind of questions like indole ring containing amino acid, or imidazole ring containing amino acid, or pyrrolidine containing amino acid, or phenol ring containing amino acid. So you need to identify them. Okay. Yeah. So these are what? We have naphthalene, anthracene and phenanthracene. All these three are aromatic. Okay, and you know, if I consider for a single ring, I already discussed this, I have single aromatic ring and a 2 aromatic rings, and next 3 I am taking anthracene. Okay, this is naphthalene, anthracene, benzene. So condensed benzene rings are there here. So now if I ask aromatic nature, you will be answering like this. That is correct only. But if you want to compare the aromaticity per the ring, for one ring, so 3 are there now. So it means 2 are there now. So 2, whatever the aromatic number it has, by 2 if you do, and here some value by 3 you need to do. That if you compare per ring aromaticity, that case benzene will be having more aromatic nature than the other. Okay, if I compare single individual rings, but overall more the number of rings, more is the aromaticity. Okay, yeah. And here 7 member ring here. Now we discuss 3, 4, 5, 6 over 7 member ring. See here you should call this as tropylium cation. So tropylium cation, tell me aromatic or non-aromatic? 6 pi electron cyclic planar, 6 pi electron with complete conjugation like this. Okay, so it means it is having 6 pi electrons, so aromatic. Tropylium cation is aromatic. So will it forms precipitate if I take propylium chloride? Propylium chloride I am taking. So chloride, will it precipitate with the HCl? Yes. Okay, yeah, like that. And this one cyclopentadienyl anion we discussed. So this one also discussed. So the compounds like this are called as quasi-aromatic. Okay, so aromatic compounds in which positive or negative charge is present is a part of Huckel rule. That complete thing is part of Huckel rule, considered as quasi-aromatic compounds. And this one, if you look, so look at this. How many electrons you are seeing in this?
5 electrons. 1, 2, 3, 4, 5, 6, 7, 16 by electrons.
So 16 means what you will think? Aromatic, non-aromatic, like that.
No, sir, anti-aromatic.
So you will be thinking like it is anti-aromatic. But these electrons which are in the center here won't participate in conjugation. Only this terminal, this 2, 4, 6, 8, 10, 12, 14 will be involving. So it is having aromatic Huckel number now. So pyrene is an aromatic compound. Just remember this. Okay, pyrene is an aromatic compound. Okay, next. See, and one more thing. Seven membered over now previously. Tropylium cation anion we discussed. Now I am writing a 8 membered ring like this. Okay, and 1, 2, 3, 4. So what is the name of this compound? Cyclic ring now. So cyclo. How many? 8. Octa. And how many double bonds? Pi bonds? 4. Octa tetraene. Cyclo octa tetraene. So in the short form I am saying COT, cot. Okay. So now these, tell me whether it is aromatic, non-aromatic based on your understanding.
It has 8 pi electrons.
Okay.
All are sp hybridized, sir.
Okay.
It has complete conjugation, but then it has 8 pi electrons, so it is anti-aromatic.
It looks like anti-aromatic, right?
Yes,
But it is non-aromatic. Why? Because in reality these compounds exist in tub form, tub shape, like this. Okay, so one by one, here, here and here. So you can just remember cot have tub shape. Okay, so this makes it to be non-aromatic. Okay, these are some exceptional cases that I wanted to discuss. Okay, yeah, this is clear now. Yeah, next one. Yeah, so one more thing, when you have a single ring with multiple pi bonds, I am saying single ring with multiple pi bonds, these kind of compounds are called annulenes. What I am saying? Annuline. Okay, so now how many carbons are there here?
8 carbons.
So you just say it as 8 annuline. Okay, so cyclic conjugated polyenes are called annulenes. What are annulenes? Cyclic polyenes. So poly, more than one or two pi bonds are there now. So cyclic conjugated polyenes are called annulenes. Number of carbons, put it in the bracket, that will be 8 annuline, means you should remind this. Okay. Now what is the name of this compound, I can say? So it is single ring now. So cyclic poly conjugated ene. So what I can say? Cyclic conjugated polyene. So with the 10 carbons now, so 10 annuline. So 10 annuline is aromatic or non-aromatic? What you are saying? Tell me. So if you look it like this, you will be having 10 pi electrons, so you might be feeling it will be aromatic. But you know, so due to the presence of this hydrogen here and here, the flag like interaction, the hydrogen bond, like flags you can remember, just they will having repulsive interactions. So due to that, what happens is this carbon comes up and this will goes down and makes it to be non-planar. Therefore it becomes non-aromatic. What I am saying, this is non-aromatic. Okay. So try to make complete notes of whatever we discussed today. You might be seeing a question from these or the derivatives of these compounds. Yeah. Next, stability of alicyclic compounds. It means we have normal non-aromatic compounds. Now, see whether, tell me whether it is aromatic or non-aromatic. Non-aromatic. There is no pi electrons to say conjugation and all. So these are non-aromatic. So they will ask what is the stability order. So it will be like this: 6-membered, more stable than 5-membered, and 4-membered, and least is for 3-membered. Okay. So why it is so? Because see in this alicyclic compounds, if you compare, if you analyze these carbons, what is the carbon hybridization in this case? sp3 carbon, having all the carbons here are sp3. I am not discussing about aromaticity, this is the other topic here, I can say. So alicyclic, not about aromatic. Aromatic is over up to here. So I am discussing alicyclic cations. So in this case, what is the carbon hybridization of this sp3? sp3 hybridized carbon means what is the bond angle we should have? 109.5 degree. Okay. But if you observe in cyclopropyl ring, so what is the angle here in the triangle? 60 degrees. So but it should contain 109, but what actually here it is 60. So this makes it to be highly strained right now. So it has to be ideally 109.5, but it is having only 60. So due to this, there is a high bond angle strain which makes it to be highly unstable. So that's why cyclopropyl is least stable, then cyclobutane or butyl carbocation and pentyl carbocation, and here cyclohexyl carbocation. Is that clear? Right. Yeah. Next, so I can say stability inversely proportional to strain. Can write this. Yeah. Next. Now look at this. There is one more exceptional thing here to discuss. I mean, what is the use of studying this you might be having? See, you might be having a question that what is the use of studying this? Like, let us look at here again. Giving NH2, so you just wanted to treat this with HNO2. Okay, HNO2 and little heating required. So what is the product formed here? Okay, so this is first hydrolysis. Okay, so what is the product formed during this reaction, they will ask. So now tell me, in the given compound, what is the reactive site? NH2. See, NH2 having lone pair electrons, this is acid, this is a base. Okay, therefore acid base reaction takes place first. After heating, that water eliminates from there and it forms a diazonium salt here. First it will forms what? Diazonium salt. Here I am writing. Let me start from here, HNO2. Okay, so here you are going to get, means the nitrogen makes one more bond with nitrogen like this. So simply I can represent it as N2 place. Okay, so this N2 place, see we know nitrogen gas is highly stable because of its 3 bond order between nitrogen. That's why it can be very inert, used as an inert atmosphere during the chemical reactions. Nitrogen is used to create a inert atmosphere also due to its high stability. So whenever you heat this, what happens? You are heating this. Okay, what happens? N2 gas will comes out between carbon and nitrogen, which is electronegative? Nitrogen. So takes the bonded electrons with nitrogen, and what you are going to get here on this carbon? Positive charge. So you are going to get something like this, CH2 positive charge, right now. So we know CH2 positive charge is there. So we know from the above discussion, from this above conclusion, that reactivity, like stability order, we know cyclic 4-membered ring means what is the angle you are? 90 degrees, but the ideal bond angle of sp3 carbon should be but 90. It is also having strain now. So now this species always try to relieve that strain. So how can it will be relieved? See, if it is expanding from here to here, ring expansion taking place. So what happens? The 4-membered ring becoming a 5-membered ring. Something like I can write a 5-membered ring. So for understanding, I just wanted to number it. So 1, 2, 3, 4, 5. Consider this is 1, 2, 3, 4, 5. So now you are seeing positive charge on first carbon. Now it is making a bond with the 5th carbon. See, 5 and 1. Between 5 and 1 we made a bond. But from where the bond is getting disconnected? From 2, carbon number 2. It means it is losing the electrons now. So it means now the positive charge comes on second carbon, like this, right now. So now here what we have other thing here? Water. So you can add water here as a nucleophile, so that we are going to get OH. That's it. This will be our product. Okay. So what you have seen, the rearrangement or the ring expansion is taking place. Whenever you have highly strained ring, expansion of ring takes place. Okay, is this clear? Yeah. This is also very important, and actually this is a IIT JAM chemistry question. I just wanted to explain here. I mean IIT JAM chemistry means chemistry question paper, yeah, that's CY. Yeah. Next one. So look at here. So one more exceptional thing is there here. When I compare benzyl and cyclopropyl carbocation, how can we give the stability order? See, we know generally if I compare normal cyclic non-aromatic compounds like this one with these aromatic compounds like benzyl rings and all, so these aromatic compounds are highly stable when we compare with this non-aromatic, okay, because of their strain and all. Okay, now this one is also looking like cyclopropyl is also looking like small ring with strain, okay, but you know positive charge present at what carbon here? Outside carbon, like here, and we have a strained 3-membered ring here. Now this carbocation is getting benefited from the strain of the ring. What do we mean by that? So due to the strain in this ring, what happens? They are very ready to, they have more tendency, are ready to open up the ring. Yes or no? Yeah. So and this fellow is also looking for someone who can give the electrons. Therefore the like the sigma bond from here will shift from here to the empty orbital of carbon. So you are going to get something like this CH2 plus is there now. So there it is shifting like this, like this. So this carbon should contain positive charge. Like this, you can shift this bond and this bond. Something like this sigma bond is dancing from here to here. So you can say dancing resonance for understanding, for remembering purpose. Okay? Yeah. So due to this dancing resonance or the conjugation of this sigma bond from here to here, this cyclopropyl like this species is getting more stabilized when we compare with the normal mesomeric effect also. Okay, this carbocation is more stable. Now again, sir, how can we use this example for understanding purpose? So look at here, I have same explanation here. So now I am using N2 here or NH2 here. So if I treat with NaNO2 or HNO2 in acidic medium like HCl, under heating condition. So what happens, first it converts into N2 plus, and if I want to add water, so and heating now, heating means this goes out now. So what you are going to get here, generally you are going to get this positive charge. Now I am giving you water, but that water won't attack directly there, ring stabilization takes place. Now either we know 4-member ring is highly strained, okay. So is there any possible for ring expansion? Expansion means 5-member, 6-member, is that possible? No. Now I just given you now here, this is relatively more stable than this 4-member. Now this undergoes a ring compression. So why ring compression? Because if this positive charge is out of the ring, that is getting stabilized, but here it is getting unstabilized. So now what happens is, so one of these bond, see I am leaving this bond, I am taking bond from here and I am adding here. So what we are going to get, see 1, 2, 3, 4. So you are getting a new bond from between 3 and 1, okay. So like this you are going to get a new bond. Just imagine what is happening, see you are having a bond between 1, 2, 3 like this, and you have 4th carbon here like CH2 like this. Now which carbon is losing? 4th carbon losing its bond now, so should have positive charge. So if I want to write the structure properly, you can have structure something like this. Like this, yes or no? Is this both are same or not? Yes. So I am writing it like this, okay. So to this is more stable carbocation when I compare with cyclobutyl carbocation. So add H2O to this, so that will be attacks here. So this is also the common MSc level questions based on your BSc understanding, okay. So yeah, so these are the 2 notable reactions you should remember from rearrangement, okay. Next, now instead of having these rings, normally if we, like normal chemical reaction, rearrangement reactions are taking place. So who will be having more migrating tendency? So generally if you have hydride ion, I means hydrogen atom, that will migrate in preference to phenyl and alkyl. So again in alkyl groups you have tertiary, secondary, primary. So tertiary having more tendency to undergo migration. It means what? Again look at here. So let us take this, like this I am writing, and here I have OH, okay. You just tell me, if I add water to this, I mean to this alcohol I am adding some acid like HBr. Now tell me what happens. This is an acid I am saying now. So this acid releases proton. This will be now attacked at this OH group. Now it becomes a water, right now, like O, already hydrogen is there and one more hydrogen you are adding. So positive charge it will be now, okay. Now what happens? Now water is formed. So when water is formed, easily it undergoes dehydration, okay. So it comes out as a water. Water is a good leaving group here, okay, like this. So now what is the charge you are seeing? Here positive charge is there. We know what type of carbocation it is. What type of carbocation? Carbon with how many carbons attached? Carbon having positive charges attached to this side one carbon, this side. So I can say it is a secondary carbocation. Now we know what is the order of stability of carbocations? 3 degree, 2 degree, 1 degree. Right now, so it means we have 2 degree carbocation. This can be stabilized more effectively by rearrangement or the hydride shift. See what I am shifting here, hydrogen atom we have and methyl groups also, alkyl groups also there. So what is the migrating tendency? Hydride group is having more tendency. So these hydrogen shift from here to here and you are going to get a hydrogen atom here like this. But hydrogen atom when it is shifting, taking the bonded electrons with itself only now. So what is the charge we should put on this carbon? positive charge. Okay, that's it. So you got a tertiary carbocation. What is this process called? Rearrangement. Okay, so carbocation rearrangement you should say. So to this what you need to add now? Out of this HBr we got H out, now we have Br, bromide ion is there, na? That will be our nucleophile attacks here to form a compound here like Br, that's it. This will be our final product. Clear? Yeah. So in the exam, you know, they will give this and they will give two options. The first option will be definitely this one. And second option might be like this or some other things. So out of these, which is major they will ask. This will be the major. Like that they make questions. Okay, this is a simple question I have mentioned, but you know, we can have lot of discussion on this. For example, I can give so major. What is the major product here in this reaction? See, you are not kids to explain everything like a 12th class or 11th class student. Just tell me what is the nature of HBr I told you in the previous acidic. It releases H plus ion. Now that H plus ion attacks where in this compound? What is the reactive site we have? Double bond. Okay. So either it should attack on benzene ring or on the double bond. But we know benzene is more stable, so it won't react. First of all, preference more reactivity is for double bond. So now you just add this H plus ion to this double bond. But where we need to add? Either on this carbon or that carbon. If you so just imagine you are adding on both sides, okay, and write the respective products that are comes from both of them. What are the species formed? If I add H plus to this terminal carbon, I am adding these. So this carbon should get because these bonded electrons are moving. So means here positive charge. Okay, and this carbon is having now SCH2 and one new hydrogen is added, CH3. If the second scenario, what is the second scenario? Yeah. So I can add H here and this will be having now positive charge. Tell me, out of these two carbocations, which is stable? This one is more stable. So which will forms? This one forms readily. Okay. So addition of HBr should be analyzed like this. Okay. So I am removing this now. Okay. Now again, after forming this, we know this is a secondary one. From this we can get a more stable carbocation. Is there any possibility again? Secondary is stable when I compare with the primary, that is good enough. After this, yeah, if I shift this hydrogen from here to here, yes, CH3, and here you have one hydrogen with a positive charge here, right now? Yeah, so this is a tertiary carbocation, which is more stable out of these two? Third one, that's where rearrangement takes place. Further you add bromide ion there. So your answer will be Br. That's it. This will be your major. Clear? Right. So now this is about the session. I just wanted to add few questions as a practice. So just tell me your answers here. So 14 aniline. What about the nature of this 14 aniline? Aromatic, non-aromatic, anti-aromatic. Try to identify. And next, whether it is aromatic or what. So just tell me. Okay, first question over. Second one, I just want to add major product. And one JAM question itself I am adding again. So if you try this, then I can consider, yeah, you are really doing well. You followed the class perfectly, I can consider. What is the major products? Will they precipitate or not? From these two. Will these chlorines precipitate or not? Okay, yeah. So I just wanted to make a question here itself. So don't scare by looking at the structures first. I just wanted to make it, wantedly I am making this much big. Consider these are hypothetical compounds. I am not talking about their existence and all, but whether they will form precipitate or not. If forms, here number of chloride ions precipitate with AgNO3, with AgNO3. It means only one chloride ion is precipitating, means you write your answer as 1, like a numerical answer type you can consider. If 2 are precipitating, give 2. If all 3, tell me 3 in the comment box. So that's it. It is about the session, and if you really like the content, just click on the like button, and if you are new to this channel, just click on the subscribe button, and you can write your feedback in the comment box. Thank you for watching.